Hi, good day. I'm here to discuss jamovi, which is a free and user-friendly statistical software that has been gaining popularity among researchers, educators, and students. It was developed with the goal of making statistics accessible and easy to use. Here's why jamovi is useful in research. You look at the interface. It is user-friendly and it looks like Excel. So entering and managing data feels familiar. Built-in analysis with just a few clicks, we can perform we can perform descriptive statistics, correlation, ANOVA, t-tests, regression, and even advanced analysis without needing complicated syntax. It is open source and free, which is unlike SPSS, which requires costly licenses. Jamovi is completely free and open source, which means anyone can download and use it without restriction. Every analysis you run in jamovi stays in your output window. If you update your data, results automatically update as well, making research transparent and efficient. Expandable modules. We can add extra modules from the jamovi library, such as JPower for power analysis or SEM modules for structural equation modeling. So in short, jamovi is more than just a statistical tool. It's designed to help us focus on interpreting results rather than struggling with technicalities. Now let us discuss levels of measurement. Before we start analyzing our data in jamovi, it's very important that we set the correct level of measurement for each variable. This tells the software how to treat the data and which statistical tests are appropriate. In jamovi, there are four main levels of measurement: nominal, ordinal, continuous, and ID. Nominal level of measurement are categories without order, for example, sex, blood type, or civil status. If I encode this in jamovi, the software knows that these are just labels, not quantities. Ordinal. These are ranked categories with a natural order, but the distance between them is not equal. A good example is Likert scale responses, such as strongly disagree to strongly agree. jamovi will recognize the order but won't assume equal spacing. Continuous or scale or interval or ratio. These are numerical values where the distances are meaningful. Examples are test scores, the mean of test scores. jamovi will allow us to compute means, standard deviations, and run parametric tests on this. The fourth one is ID. This is not usually for analysis but for identification cases such as assigning participant numbers. When we input data in jamovi, we can see the measure type beside each variable name. By clicking the icon, we can change it, for example, from nominal to ordinal, or from ordinal to continuous. This step is crucial because if we set the wrong level of measurement, jamovi might run the wrong test or misinterpret our variable. So in summary, always check: is my variable categorical, ordinal, or continuous? Once that's properly set in jamovi, we can be confident that the analysis will give correct and meaningful results. Now that we know how to enter data in jamovi, let's talk about coding. Coding simply means assigning numbers or labels to responses so jamovi can understand and analyze them correctly. In jamovi, we can do this directly in the data view. Each column is a variable and each row is a participant's response. So for example, we have a variable here and about gender. And gender is a nominal type of data. Suppose our survey asks what is your gender with choices male and female. Instead of typing the full words repeatedly, we can code them as 1 is to male and 2 is to female. In jamovi, we click the variable name, go to data tab. Under levels, we need to define 1 equals male and 2 equals female. Now when we type 1 or 2, jamovi will display male or female in the cell. Example number 2, Likert scale. If our questionnaire has items like I am satisfied with my job with choices from strongly disagree to strongly agree, then in jamovi, we set this variable as ordinal and define these labels under levels. This helps jamovi recognize that the responses are ordered. This is question 1. I'll set this to ordinal. And 1 is to strongly agree. Two is disagree. This is strongly disagree. 3 is neutral. 4 is agree. And 5 is strongly agree. Why coding matters? Correct coding tells jamovi how to treat the variable, categorical, ordinal, or continuous. It also makes our dataset cleaner and easier to analyze, and when we run analysis, results will show meaningful labels like male or agree instead of raw numbers. So in summary, coding is simply translating survey responses into numbers and labels, and jamovi makes this process smooth by letting us define levels and measurement types for each variable. Once we have encoded our data properly in jamovi, the next step is usually to look at the descriptive statistics. Descriptives help us summarize and understand the basic features of our data before we move on to more advanced analysis. In jamovi, we can do this by going to the top menu, clicking Analysis, Exploration, Descriptives. Here's what we usually highlight. Let's have here an example for continuous variables, salary, and parent income. Jamovi provides measures of central tendency, such as mean and median, and measures of variability like standard deviation, minimum, maximum, and range. For example, um, here we have here the descriptives of salary and parent income, which shows in salary uh, a population of 10 for both salary and parent income. There are no missing values, so all data points were included in the analysis. Let's go to measures of central tendency. The mean of the salary is 29.9 and median of 27.5. Mode is 15. Mode. Mode. Go and check the mode. Now it says that there are more than one mode exists and only the first one is reported. So mode of the salary is 15, but jamovi is showing only one. The mean and median are close, suggesting the data is fairly balanced. The parent income, the mean is 26.1 and the median is 27.5. Mode is 20 and there are also more than one mode that exists. The mean is slightly lower, 26.1, than the median, hinting at a small negative skew. A few lower values may be pulling the mean down. Let's go to the measures of variability for the salary. The standard deviation is 11.2. The variance is variance. The variance is 125 and the range is 35, which is from 15 to 50. In the parent income, the standard deviation is 7.8, slightly less spread compared to salary. The variance is 60.8. Range is 24, which is from 12 to 36. This tells us that salaries vary more widely than parent incomes in this sample. Its minimum and maximum salary ranges from 15 to 50 and parent income ranges from 12 to 36. Now let's take a look at the normality by clicking Shapiro-Wilk. The Shapiro-Wilk of the salary is 0.938 and a Shapiro p-value of 0.530, and the parent income Shapiro-Wilk is 0.934 with a p-value of 0.491. Since both p-values are greater than 0.05, we fail to reject the null hypothesis of normality. This means both variables, if they are greater than 0.05, means they are approximately normally distributed. Both variables, salary and parent income, are normally distributed as evidenced by a Shapiro-Wilk p-value of greater than 0.05. The salaries tend to be slightly higher and more variable compared to the parent incomes. And both datasets have multiple modes which suggest clustering of responses around different points. The spread of salaries is wider, which is 35, than that of the parent income, which is 24. So this is how we're going to take a look at the descriptives of the variables. Another thing for us to check is the normality by shape. So we can check the histogram and the density. So we can see here that there is a bell curve, and as evidenced by this variable p, the normality, this suggests that normality is normal. But we understand our data. Let's move to testing relationships using the correlation coefficient. Correlation tells us whether two variables move together and how strong that relationship is. In jamovi, we usually use Pearson's correlation if both variables are continuous and normally distributed, and Spearman's correlation if the data are ordinal or not normally distributed. Here's how we do it. Go to Analysis, Regression, and click on Correlation Matrix. Select the two variables you want to test. So in this case, we'll be testing salary and parent income. And let us interpret the correlation coefficient. Now, the value of R ranges from -1 to +1, and R close to +1 means a strong positive relationship. As one increases, the other increases. And R close to -1 means a strong negative relationship. As one increases, the other decreases. And R near 0 means little to no relationship. So in our variable parent income and salary, the R value is 0.620, hinting that there is a positive relationship. And let's take a look at the p-value. This tells us whether the correlation is statistically significant. If p is less or equal than 0.05, or no, if p rather is less than 0.05, we reject the null hypothesis, which says there is no relationship, and conclude that there is a significant correlation between the variables. If the p-value is greater or equal than 0.05, then we fail to reject the null, meaning the correlation is not statistically significant. So in this case, what we see here is a p-value of 0.056, which is greater than 0.05. So this means to say that we fail to reject the null, meaning the correlation is not statistically significant. Now, we use Pearson if there is no violation on the assumption of normality, and if there is a violation on the assumption of normality or the other assumptions, then we'll be using Spearman to perform a non-parametric test. But since our test for normality is well distributed, then we'll be using a parametric test, which is Pearson R. So again, let me reiterate a value of a p-value of less than 0.05, we reject the null hypothesis, which says there is no relationship, and conclude that there is a significant correlation between the variables. If the p-value is greater or equal than 0.05, then we fail to reject the null, meaning the correlation is not statistically significant. First things we need to establish is whether it is reliable. Reliability means that the instrument consistently measures the concept we want to study. In jamovi, we can check reliability using two main statistics, Cronbach's alpha and McDonald's omega. Cronbach's alpha is the most widely used measure of internal consistency, and in jamovi, we can go to analysis, factor, reliability analysis, then select the items that belong to the same construct. An alpha value ranges from 0 to 1. A value of greater or equal than 0.70 is acceptable, greater or equal than 0.80 is good, greater or equal than 0.90 is excellent. So in our case here, we can conclude that the instrument we are using is reliable because the scale of the Cronbach alpha is 0.804, suggesting that the instrument is instrument's reliability is good. Omega is also considered a more robust and modern alternative to alpha. So you can click and also check McDonald's omega. The interpretation is similar to alpha with the same cutoffs. 0.70 acceptable, 0.80 good, and 0.90 is excellent. Omega is especially useful when items have different factor loadings or when the assumption of tau equivalence for alpha is not met. If Cronbach's alpha is 0.804 and McDonald's omega is 0.85, then we can say that the instrument shows good internal consistency supported by both alpha and omega. This suggests that the items are reliably measuring the intended construct. Before we conduct any study, we need to determine how many participants are enough to detect meaningful results. This is where power analysis comes in. Power analysis helps us answer the question, how big should my sample size be? It balances three elements: the effect size, the strength of the relationship or difference we expect, the significance level, alpha, usually set at 0.05. This is the risk we accept for making a type 1 error. The power, 1 minus beta, the probability of correctly rejecting the null hypothesis, usually set at 0.80 or 80%. This means we want an 80% chance of detecting a real effect if it exists. In jamovi, we can run a power analysis through the J-power module. Click on power, click on correlation, okay, and enter the expected effect size, desired alpha level, and power. Then jamovi will compute the required sample size. Now, the most accurate thing to do in entering the effect size is to refer to prior studies. If prior studies will say that they use 0.3 for a medium effect size, then you can use that one as your effect size as well. The minimum desired power is 80 and the significance alpha is 0.05 for a two-tailed test. Then I'll be getting a minimum sample size of 84. Now, if there are no prior studies, you can use the Cohen's guideline. And Cohen's guideline is saying that you can use a small effect size. But if you use a small effect size, take note of what will happen to your minimum sample size. From 84, it will increase to 193 for you to detect a true effect. And if you use a large effect size, then your minimum sample size will be 28.